Good morning dear students. In the last video we learnt electric field intensity due to a point charge, electric lines of force, properties of electric lines of force, electric dipole and electric dipole moment. In this class let us concentrate on few more concepts. In that first one, electric flux. Electric flux is represented by phi. Look at the statement. The total number of electric field lines passing normally through the given surface. So this is the statement for electric flux. Look at the diagram. In order to understand electric flux, we need to know what exactly the electric field lines or electric lines of force. About the electric lines of force, in the last video only we learnt what exactly the electric lines of force. Look at this diagram. So these are all electric lines of force. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electric field lines or electric lines of force I consider. Inside the uniform electric field I kept surface area, rectangular surface area. So look at this diagram. 1, 2, 3, 4, 5, 6, 7, 8. Out of 8 electric field lines, 1, 2, 3, 4. There are only 4 electric lines of force passing normally through the given surface. So these bundles of electric lines of force which are passing normally through the given surface is known as electric flux. Look at the diagram. 1, 2, 3, 4, 5, 6, 7, 8. Out of 8 lines, 1, 2, 3, 4. Only 4 lines are passing normally through the given surface. So these bundles of electric lines of force are said to be electric flux. So we can understand the electric flux by using 3 steps. Step 1. Electric flux is directly proportional to the electric field, which means when the electric field is stronger, electric flux is maximum. While discussing properties of electric field lines, we studied that when the electric field is stronger, the electric lines of force are crowded, which means when the electric field is stronger, a maximum number of electric field lines passing through the given surface. As the maximum number of electric field lines passing through the given surface, electric flux is maximum. First step. Move to the second. See the second step. Electric flux is proportional to surface area. Electric flux is also depends on surface area. See here I consider 2 surface areas. So for this I can give a name as A1. For this I can give a name as A2. So look at this. A1 is small compared to the A2. Through the A1 only there are 2 electric field lines are passing. Look at the second surface A2. Through the second surface 1, 2, 3, 4, 5. There are 5 electric field lines are passing, which means it is directly proportional to surface area. Look at this. Here only there are 2 electric field lines are passing through the given surface, that is A1. Since it is very bigger compared to the A1, say 1, 2, 3, 4, 5. There are 5 electric field lines passing through the given surface. So that electric flux is directly proportional to area. And third step, flux is directly proportional to cos theta. Electric flux is also depends on angle theta. See this diagram. These are the electric field lines passing through the given surface. Here one thing you can observe, A vector or vector A. Area vector. Vector A or A vector is called as area vector. What exactly the area vector? Area vector is nothing but the straight line drawn perpendicular to the area element. So this is the area element. To this area element I am drawing straight line perpendicular to the area element. That straight line is known as area vector. So here the angle between the electric field and area vector is 0, which means electric field lines are perpendicular to the given surface. When they are perpendicular to the given surface, angle between electric field and area vector is 0. When theta is 0, electric flux is maximum. We have one more diagram. You just see this diagram here. 1, 2, 3, 4, 5. There are 5 electric field lines. One more thing you can notice here, this is area vector. So here the angle between electric field and area vector is 90 degree. When theta is equal to 90 degree, electric flux is 0, which means electric field lines are parallel to the given surface. So these are the 3 steps to understand electric flux. Electric flux is directly proportional to electric field. Electric flux is directly proportional to area. Electric flux is directly proportional to cos theta. So by using these 3 steps, I can make one equation, that is phi directly proportional to E A cos theta. And we can cancel this proportionality by using a constant. If that constant is 1, then equation become E A cos theta. So this is a general equation to calculate electric flux. We can express in terms of vector form. In vector form, we can write phi is equal to A vector dot A vector. Product of two vector is scalar. So electric flux is scalar quantity. And SI unit is, look at the SI unit. SI unit of electric field is Newton per Coulomb, and SI unit of area is meter square. So Newton meter square per Coulomb or Newton meter square Coulomb inverse. Look at this statement for electric flux. How does the electric flux varies with electric field, area and angle theta? And by using these 3 steps, we made one equation, that is phi is equal to E A cos theta. In vector form, we have phi is equal to vector E dot vector A. The product of two vector is scalar, so electric flux is a scalar quantity. SI unit is Newton meter square per Coulomb or Newton meter square Coulomb inverse. We have one more method to understand electric flux. Let us discuss that method also. According to that method, look at the statement. It can be defined as product of component of electric field along the normal and area vector. So by using this statement, I am going to explain electric flux now. I consider area element, electric field theta. So this is the area element, and we have a theta. Theta is angle between electric field and area element, that is delta A. According to this statement, electric flux can be defined as product of component of electric field along the normal and area element. Here we don't know what exactly the component of electric field along the normal. The component of electric field along the normal can be understood by using resolution of vector, what we studied in the first PUC. For example, I am taking a R vector is resolved into two components, vertical component and horizontal component. This R vector, I'll write it diagonal. This R vector is resolved into two components. Along horizontal it become R cos theta, along vertical it become R sin theta. Similarly, here the electric field is resolved into two components, This electric field resolved into two components, along horizontal E cos theta, along vertical E sin theta. So here component of electric field along the normal means along the normal. So according to this diagram, E cos theta find as product. So by using this statement, we can write the equation electric flux. Component of electric field along the normal is E cos theta and area element is delta A. So we can write like this, E delta A cos theta. Since we are talking about the area element, it would be delta phi. This represent electric flux through area element. To calculate total electric flux through the given surface, through any given surface, I'll write here total electric flux, that is phi, through any given surface is given by phi is equal to summation of delta phi. So phi is equal to summation of delta phi. What we have for delta phi? E delta A cos theta. Final expression we can express in terms of vector form. In vector form, summation of A vector dot A vector. As I said in the beginning, electric flux is scalar quantity. SI unit is Newton meter square per Coulomb. And we have two cases by using this equation. Case 1, when theta is equal to 0 degree, phi is equal to summation of E delta A cos 0 degree. Cos 0 is 1. So the remaining equation phi is equal to summation of E into delta A, that is maximum electric flux. Case number 2, when theta is equal to 90 degree, same equation I am using, phi is equal to summation of E delta A cos 90. Cos 90 is 0. So flux through the given surface is 0. So this is second method to understand electric flux. Next concept is electric field at a point on the axial line of the electric dipole. It's a very important for 5 marks. It was asked in the year March 2016 and June 2017. That is a supplementary paper. So before going to the derivation, we need to know what exactly the electric dipole and axial line. In the last class itself, I explained what is electric dipole and axial line. We will recall, electric dipole is nothing but a pair of equal and opposite charges separated by a certain distance 2a. Look at this, negative charge, positive charge separated by a distance 2a. So I consider electric dipole. Then what exactly the axial line? The straight line joining negative charge and positive charge, and it can be extend on either side, which means it can extend on negative charge side also, it can extend on positive charge side also. So I extended on positive charge side. Look at this straight line, what I marked by using a white chalk, that is nothing but axial line of the electric dipole. Our intention is to find electric field at a point on the axial line. So we have to mark one point on the axial line of the electric dipole. So this is the axial line of the electric dipole. I marked the point, I have given the name as P. And here one more thing you can notice, this is the midpoint of the electric dipole, and P vector is electric dipole moment. In the last class we learnt the direction of electric dipole moment is from negative charge to the positive charge. Look at the arrow mark. And this is the midpoint of the dipole, and this 2a can be written as from here to here it is a, from here to here it is a. And the distance between the midpoint of the dipole and the point where I marked on the axial line is taken as r. And about this, E plus Q, E minus Q, E is equal to E plus Q plus E minus Q, you will get to know during the explanation. So let us start with the explanation. Now our intention is we are finding the electric field at a point P due to electric dipole. This is the electric dipole. Now electric field at a point B due to negative charge, that is a minus Q, can be written as E minus Q. Electric field at a point P due to negative charge can be written as E minus Q. We know that the direction of electric field in case of negative source charge is directed inwards. Directed inwards. Look at the direction. Directed inwards. Since we are talking about the negative charge, I will write minus. According to the Coulomb's law, 1 over 4 pi epsilon naught. Already I have taken minus, the remaining is Q. Here 1 Coulomb, that is into 1, it become Q only, divided by what is the distance between a minus Q and the point P. The distance from here to here it is R, from here to here it is A. So total it become R plus A according to the Coulomb's law whole square, equation number 1. This equation gives electric field at a point P due to negative charge. Similarly, electric field at a point P due to positive charge can be written as E plus Q. Since it is a positive charge, positive, same thing, 1 over 4 pi epsilon naught Q divided by, look at the distance between the positive charge and the P is R minus A whole squared, equation number 2. So equation number 2 gives electric field intensity at a point P due to positive charge, and we know that the direction of electric field in case of positive charge is directed outwards. See, look at the direction, directed outwards. Now by using these two equations, we are calculating resultant electric field at a point P due to electric dipole. Resultant is nothing but total electric field. So to identify the total electric field, I will write E resultant. E resultant is equal to, we need to add both, E plus Q plus E minus Q. So I will write only E, I won't write E resultant, it's understood. E plus Q is, what is the value for E plus Q? 1 over 4 pi epsilon naught q divided by r minus a whole square plus within a bracket, why? Because we have a negative sign here, minus 1 over 4 pi epsilon naught q divided by r plus a whole square. Next step, E is equal to 1 over 4 pi epsilon naught q divided by r minus a whole square plus into minus 1 over 4 pi epsilon naught q divided by r plus a whole square. Look at this equation, 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, even q we can take as a common right here by taking q divided by 4 pi epsilon naught as a common. The remaining thing 1 over r minus a whole square minus 1 over r plus a whole square. Then E is equal to q divided by 4 pi epsilon naught, we can take LCM, cross multiplication r plus a whole square into 1 r plus a whole square minus r minus a whole square into 1 r minus a whole square divided by LCM r minus a whole square into r plus a whole square. So like this we got. Now we have to solve numerator and denominator. So let us solve numerator first. A plus b whole square, this is a minus b whole square formula. So according to that formula I am writing r plus a whole square minus r minus a whole square is equal to a plus b whole square formula, r square plus a square plus 2 r a minus is there, let it be minus r minus a whole square, a minus b whole square formula, that is r square plus a square minus 2 into r a, r square plus a square plus 2 into r a minus into plus minus r square minus into plus minus a square minus into minus plus 2 into r a. So plus r squared minus r squared get cancelled, plus a squared minus a squared get cancelled. So 2 r a plus 2 r a become 4 into r a. So in the place of r minus a whole square minus r minus a whole square we can write 4 r a. So like this we can solve denominator also. So a minus b into a plus b can be written as a square minus b square. Similarly we can write it for r plus a whole square can be written as r square minus a square, since it is square is there it become whole square. Now we simplified the numerator and denominator, I am going to substitute. E is equal to q divided by 4 pi epsilon naught, numerator is 4 into r a divided by denominator is r square minus a square whole square. Now I am taking q to the right hand side, means to this within the bracket it become 1 over 4 pi epsilon naught q. Instead of writing 4 I will write into 2r. Look at this simplification carefully. Q have taken within the bracket and instead of 4 have written 2 into 2. So 4 only, a we have a r we have a r. But Q into 2A is nothing but P. It is nothing but electric dipole moment. We studied in the last class itself. So E is equal to 1 over 4 pi epsilon naught. In the place of Q into 2A I can write P, then remaining is 2R divided by R square minus A square whole square. The remaining thing I will write here. You just see the diagram. Here the dipole is very short. If the dipole is very small or short, which means R is very much greater than A. R is very much greater than A. That I will write here. If dipole is short, that is R is very much greater than A square can be neglected as compared to R square. If dipole is short, that is R is very much greater than A, look at the diagram, A square can be neglected as compared to R square. So neglect A square here. By neglecting A square, I am writing the remaining equation. E is equal to 1 over 4 pi epsilon naught. P2R can be written as 2PR, that is also correct, divided by, we are neglecting A square, the remaining thing is R square whole square. Then 1 over 4 pi epsilon naught 2PR divided by R square whole square means R to the power of 4. Here R and 1R cancel, the remaining is 3. E is equal to 1 over 4 pi epsilon naught 2p divided by R to the power of 3. So this is the final equation which gives the magnitude of electric field at a point on the axial line of electric dipole. So in this point we are getting E is equal to 1 over 4 pi epsilon naught 2p divided by RQ. This is in terms of magnitude. So this equation clearly says that the electric field and the electric dipole moment are in same direction. Look at the direction. This is the direction of electric field and this is the direction of electric dipole moment. Both are in same direction. We can express this equation in terms of vector form like this. In vector form, E vector is equal to 1 over 4 pi epsilon naught 2p divided by RQ p cap, where p cap indicates unit vector in the direction of electric field. So this is very important for 5 marks. So in this class we learned electric flux. When does the electric flux become maximum and minimum? And one more important derivation we learned, that electric field at a point on the axial line of the electric dipole. So this is the derivation. In the next class we will discuss the next derivation, the same derivation, but we are finding electric field at a point on the equatorial line of the electric dipole. Thank you.